Hi, the subject today is the second derivative test for maximums and minimums. And the big picture is it's just a new way, a different way to justify maximums and minimums. So you already have a certain way to justify these max and mins, and we haven't really given it a name because we didn't need to, but we're going to now call it the first derivative test. See this very friendly graph? Your eyeballs see a minimum at x equals 3. But to justify this AP style, you've become accustomed to carrying out what we will call the first derivative test, which is take your first derivative, find some critical values, put the critical values on the number line, test some points on either side, and then your eyeballs tell you, hey, that graph was going downhill, then uphill, must be a minimum, and then you say there's a minimum at x equals 3. You refer to the first derivative switching sign from negative to positive, and that's why you call it the first derivative test. Well, that's all old news to you. But the new news is this thing called the second derivative test for maximums and minimums. And I'm going to unveil the wording, math symbolism, and English wording. And it may or may not be a little bit clunky to you in the beginning, but don't worry, it's going to end up being pretty easy and understandable. Here's the math wording. It says, hey, we will have a maximum at some x value if the first derivative equals 0 at that x value and the second derivative is negative. You can read that one too. But let's transfer these into English language. Basically what it's saying is, if I have a horizontal tangent, because when my first derivative is 0, I have a horizontal tangent, and that horizontal tangent occurs during a concave down interval. When my second derivative is negative, I have a concave down. Well, a horizontal tangent in a concave down interval should give me a maximum. And if you look at the sketch, I drew a concave down interval, and it included a horizontal tangent, and your eyeballs tell you that's a maximum. So the second derivative test is just a different way to say there's a maximum there. You used to say, for something like this, the first derivative switched from positive to negative because the slope went from positive to negative. So likewise, if I have a minimum, there must be a horizontal tangent in a concave up stretch. A horizontal tangent in a concave up stretch leaves me a minimum. So that's what the second derivative test is. It's just a different way to justify maximums and minimums. We're going to go through two quick examples to show it in action. Let's start with the same example that we just did using the first derivative test, and let's replace our justification with the second derivative test. For the second derivative test, I need to find out where do I have my horizontal tangent. So I set my derivative equal to 0, and I find the x value at which I have a horizontal tangent. So the second part of the second derivative test is, once you know where you have a horizontal tangent, figure out what the concavity is, or the second derivative is, at that location. So now I take my first derivative, and I convert it into a second derivative. In this case, it's ridiculously easy. Since my second derivative is 2, that means my function is always concave up. So at x equals 3, I have a horizontal tangent, and it's in a concave up stretch. Look up at the graph, I have a horizontal tangent in a concave up stretch, so I have a minimum. The second derivative justification for my minimum, just like I could have done it with the first derivative test. Let's look at one more example. And here I have your friendly sine function. And because we're so familiar with it, you know there's a maximum at pi over 2, but let's pretend you didn't. If I wanted to use the second derivative test, I would move on to the first derivative, then the second derivative, because I'm going to need both of those. And I would need to know, hey, when do I have horizontal tangents? Or in other words, when is y prime equal to 0? Well, I'm kind of taking a shortcut here, but I know that at pi over 2, y prime which is cosine of pi over 2, is equal to 0. So I know that at pi over 2 I have a horizontal tangent, and at pi over 2, if I plug that pi over 2 value into the second derivative using my unit circle, I get a negative value. So these two items, the horizontal tangent, the concavity, they go together to say I have a maximum at pi over 2 because the first derivative was equal to 0 and the second derivative was negative. Or in other words, I had a horizontal tangent in a concave down stretch. So there's your second derivative, the star of the show today. I will add one little point from the math lawyers. The second derivative test is only allowed to be used for points that are on the interior of your interval. So you're not allowed to use it at an end point of any interval. So just use it on points within the interval. If you try it on an endpoint, the math lawyers will get you.